This resource is the third of a three-part series that looks at systems of equations. Part 1 defines systems of equations. It then considers the meaning of a solution to that system of equations. It looks at three examples, one of which is a word problem. Part 2 presents the substitution method of solving systems of equations. Systems of two variables are presented, as are special cases for systems of three equations. Part 3 looks at the elimination method for solving systems of equations. Systems of two variables are solved in full. We will also look at elimination for systems of three variables, but in interest of time and attention span, only the beginning steps are shown. The elimination method for solving systems of equations is both easier and more powerful than substitution. While the general method for substitution was solve and plug in, the general method for elimination is to multiply and add. Elimination helps you avoid dealing with fractions. It works for any system of equations, with any number of variables. The only condition needed for elimination is that all the equations need to have all variable terms on one side of the equal sign and the constants on the other. But how exactly does the elimination method work? Let's find out. This is the process for solving a system of two equations in two variables. After making sure all the variables are on one side, constants on the other, you have a major decision to make. Which variable do you not like and want to get rid of? I suggest you look for a variable with a mix of positive and negative coefficients. Then you crisscross those coefficients, sort of. You want to use one as is, the other with the opposite sign. Now you multiply all the way through the equations. The coefficients of the variable you are eliminating should be the same number with opposite signs. Next, you add straight down, combining like terms. This makes one variable go away. You divide to solve for one variable. Now, back substitute into an original equation. I recommend plugging into an equation with all positive coefficients, if possible. You should be left with an equation and one unknown. Solve that equation. And remember, it never hurts to check your answer by plugging into the original equations. Let's look at a couple of examples. If we look at this example, we have the system 7x minus 2y equals 44 and 5x plus 3y equals 58. Note that y has a plus in one equation and a minus in the other equation. This suggests that we should try to eliminate the y. Now we will crisscross the coefficients for y. We bring the 3 up and bring the 2 down. However, we switch the sign on the 2 to a positive. We multiply those numbers through the entire equation, including the numbers after the equal sign. Multiplying, we get 21x minus 6y equals 132, and 10x plus 6y equals 116. Note that the coefficients for y, the variable we are trying to eliminate, now match except for the signs. Add straight down. 21x plus 10x is 31x. Minus 6x plus 6x is 0, so the variable y is gone. 132 plus 116 is 248. So we are left with 31x equals 248. Divide both sides by 31. So x equals 8, but we want to have the value for y as well. So we will plug that value of 8 into the original equation that had a plus sign. Doing so, we have 5 times 8 plus 3y equals 58. Multiplying, we have 40 plus 3y equals 58. Subtract 40 from both sides of the equation. We are left with 3y equals 18. Divide both sides by 3 to solve for y. We have y equals 6. So we think our solution is x equals 8 and y equals 6. Let's check it in the equation we did not use. 7 times 8 is 56, and 2 times 6 is 12. 56 minus 12 does equal 44, so our answer checks out. But what happens if the signs are not different in our equations? Let's find out. This time, we have the system 2x plus 3y equals 73, and 5x plus 4y equals 123. We do not have a nice mix of plus and minus, so we can choose to eliminate either variable. I must truly dislike y, because I want to get rid of it again. We need to crisscross, but we need to put a minus in somewhere, so y will go away. I brought the 3 down as is, but switched the sign on the 4 and will multiply by a negative 4. Doing so, we have negative 8x minus 12y equals negative 292, and 15x plus 12y equals 369. Now the coefficients for y match up, so we can combine straight down. Negative 8x plus 15x is 7x. Negative 12y plus 12y is 0, so the variable y goes away. And negative 292 plus 369 is 77. So we are left with the equation 7x equals 77. Divide both sides by 7. So x is 11. Now we need to back substitute to find y. So we plug the 11 in for x in the first equation. We have 2 times 11 plus 3y equals 73. Multiplying, we are left with 22 plus 3y equals 73. Subtract 22 from both sides. 3y equals 51. Divide both sides by 3. So y equals 17. To check our answer, we substitute 11 for x and 17 for y in the second original equation. 5 times 11 is 55, and 4 times 17 is 68. 55 plus 68 is indeed 123, so the solution checks. How are we going to handle a problem where we have 3 equations with 3 variables? Our basic plan will be to work on 2 equations at a time to eliminate one variable completely. This will leave us a new system of 2 equations in 2 unknowns. In this example, we will eliminate z. First, we will work with the top 2 equations. 2x plus 3y plus 4z equals 36, and 5x minus 8y minus 7z equals 11. As before, we crisscross, so the 7 goes in front of the top equation, and the 4 goes in front of the other equation. Multiplying all the way through, we get 14x plus 21y plus 28z equals 252, and 20x minus 32y minus 28z equals 44. Adding straight down, the z terms cancel, and we are left with 34x minus 11y equals 296. Now we turn our attention to a different pair of equations. Again, we want to take advantage of the given minus sign. So we look at the bottom 2 equations of the original system. 5x minus 8y minus 7z equals 11, and 4x plus 9y plus 2z equals 78. We bring the coefficients of z in front of the other equation, so the 2 comes up and the 7 goes down. Multiplying through, we have 10x minus 16y minus 14z equals 22, and 28x plus 63y plus 14z equals 546. Adding straight down, the z's cancel out, and we are left with 38x plus 47y equals 568. Now we have fully eliminated the z from the problem, at least until we find the value of z at the very end. What we have remaining is a system of two equations with two variables. 34x minus 11y equals 296, and with 38x plus 47y equals 568. From here, we follow the same method as we used for the first two examples. The most mathematically powerful method of solving systems of equations is the elimination method. While the work involved is easier than the work for the substitution method, even the elimination method becomes tedious for systems of 3 or more variables. These systems can be solved, but you would want to do so using a computer. In fact, numerical analysis is the branch of mathematics that looks at how to write computer programs that solve tasks like solving systems. But I digress. The basic concept of elimination is to multiply and add. Once you have all the variable terms on one side of the equal sign and the constants on the other, you can use the solving algorithm. Pick a variable to get rid of. Crisscross the coefficients by placing them in front of the other equation, but make sure to use the opposite sign for one of the coefficients. Multiply all the way through the equation, including the constant after the equal sign. Add straight down. Divide to find the value of the remaining variable. Substitute that value into one of the original equations. Solve for the variable that you had eliminated. Then you should check your answer.